let's take a look. Let's start with the tricky ones, I guess. So, part of the homework was to do, this is something you're going to have to do a couple of times on our next quiz. And that will be sometime after Thanksgiving break, probably give ourselves at least one day coming back from Thanksgiving to review things and so forth. So maybe that Tuesday or Wednesday may be more likely. I don't know yet for sure after we get back from Thanksgiving. But all right, so we are looking for the derivative. Okay. Now, the only comment I would make, understandable, just getting started with this, you know, but we went through a few examples. Chances are pretty good we're going to go over this in class, right? We spend a decent amount of time covering at least some of the harder homework questions. However, if I really had no clue on how to get this to work in the algebra or whatever, after doing it for a day or so on a previous assignment, we had to do it. You know, I think maybe, and I knew the teacher was going to be here at like 7 o'clock, and I had this class first period, you know, I might have said, you know, I'm going to come in about 7:30. I'm going to have him go through this with me individually, because I obviously didn't pick it up yesterday when he was talking about it, and so maybe today when he goes over it, I may not get it again. Okay? I mean, just saying. It might be something you might want to think about. Okay? Because you might be thinking, man, I did good on that last quiz. My grade looks pretty good right now. But, we got to, well, it's because I'm on this thing. But anyway, all right. So, here is the definition of the derivative, right? Okay, so, here's our function, 1 over x. So we need to write this out. So what's that mean? That means plug x plus h in for x, and then plug an x in. So some of you didn't even have that part set up, right? And then some of you didn't even know that I said do this a long way, which is really strange because I wrote it out, and it says it on the homework sheet, and right, I kind of made a big deal about it. So I'm not sure how that slipped by that you didn't even know you were supposed to do that. But anyway, here we go. So you put an x plus h in here, that's 1 over x plus h. So f of x plus h would be this part, f of x would be this part, all over h. Now, we got a bow tie, right? I even told you that, right? I said, you're doing 1 over x because that's going to give you a chance to practice the bow tie. And we're going to do square root of x because that's going to give you a chance to practice what? The conjugate method, right? Those two, right? Which we had done in class, so I'm guessing you had written those down in your notes. I'm hoping you had written those down in your notes, those two methods, which could have been, okay, let me go back to my notes and let's look at those and let's see what I did there, and then let's try to mimic that here, right? I mean, so there were quite a few papers there where I didn't see that kind of attempt, but there were some that I did. Okay, so now I just went with the common denominator method, but the bow tie method said this. So you got x, and then you got minus, and then we're going to bow tie that, x plus h times 1, so that's x plus h, like so, and then that's all over what? That's all over the bottom multiplied together, x and x plus h, okay? So you are going to have to do that in problems on the next group, okay? There you go, I just told you a problem, at least one problem on the next group, okay? Like so. All right, now I think I've got that written down on the next line, so I'm going to get out of this. Okay. All right. Now I actually kept it as two separate ones here, but it would look like, okay, what I had, let me rewrite what I had a minute ago. I had this. I had already put it together, okay. When I did the common denominator, it kind of looks like that. When you bow tie, it kind of puts it all together as one, which is kind of nice. Okay, so that's the same thing, because those two together would be this. Now, you got to make sure to distribute that negative. So what are you going to get on top here? you're going to get, yeah, so the x's are going to cancel, right? So you're going to get negative h. So you're going to have negative h over x times x plus h, and then that's all over h, right? Then we're going to invert and multiply. When we invert and multiply, right here, it looks like that. Of course, I did it down here, but that just shows you you're doing that. That cancels. But I'll be honest, I usually don't write that part. I just cross that out, invert and multiply. Cancel, cancel, and we get negative 1 over x times x plus h. Right? And now we can bring in the part where we can let h go to 0. Now, I had this conversation with several people yesterday. I can't remember if it was this class or the other class. But somebody said, well, I thought you couldn't put h in. I thought you couldn't put 0 in the bottom. No. What is it we can't have on the bottom? A total of 0. We can't divide by 0. But just putting a 0 in for that h is fine. Right? You can put a 0 in for that h right there. That's fine. Because that's x plus 0, which is x, and then x times x is x squared. So that doesn't give you 0 on the bottom. Right? It's not that you can't ever have a 0 on the bottom. You can't have a total of 0 on the bottom. Okay? So you put a 0 right there, and you get negative 1 over x squared. Okay? Which is what we were looking for, because if you look at that, negative 1 over x squared would just be negative x to the negative 2. And think about what we started with. We started with 1 over x, which is x to the negative 1, and our new shortcut says we do what? Power rule says we do what? To do the derivative. Bring that down. Take off 1. Do that right there. Okay. It'll work. Okay. So this is much nicer, granted, like that. Love that power rule. Okay. But we got to be able to go through this algebra. Okay. All right. Now let's do this one. All right. Now, try that out. All right. So we said here, so now again, we got f of x plus h minus f of x all over h, which again, where does that come from? What is that right there? What did I just write right there in red? What is that? It's a definition derivative, but what else? It's slope between 2 points, right? That is slope between 2 points. One is x plus h. And then if I bring in this part, that does what? Makes them become 1 point, right? Closer and closer and closer here. Makes the 2 points become 1 point. And I get my derivative. Okay, so f of x plus h, we put an x plus h in there for x. F of x would just be an x in for x, right? Square root of x. So we get this. So we said whenever you have this radical like this, or we did the example of radical x plus 2, so we did radical x minus 2. Well, here I have a radical minus a radical, so I'm going to multiply a radical plus the radical, right? A plus b times a minus b. That's the conjugate. Whenever you see a radical in these problems, that's what you want to do, is the conjugate. Radical x minus a radical, or radical minus a radical, we're going to do radical plus a radical. Because what happens? When I FOIL this on top, what do I got? I got that times that. The square root's gone, x plus h. The outers and the inners are going to drop out. That's what a plus b and a minus b does. It's gone. And then I'm just going to have, what happened there? Then I'm going to have that times that. Square root of x times square root of x is x. That's going to be minus. And then the bottom is just h times that quantity, and I don't want to mess with that. I'm just going to leave it like that. Because I'm going to want to cancel here shortly. So I want to leave that like it is. But this I want to FOIL together because that's why I did it. A plus b times a minus b is a squared minus b squared. Good things happen there. All right, well, look what happens. The x's are going to cancel very nicely, and I'm just going to be left. These x's are going to cancel right here. I'm going to be left with just h. Now those two h's can cancel right there. There's 1 left there. And now I can put the 0 in for this h right there. Right? And so I get square root of x plus square root of x, or 2 square root of x. Right? I guess I rewrote it there again. Okay. I'm going to put my 0 in, right, after I cancel those h's. Put my 0 in. So I get 1 over 2 square root of x, right? Which, another way to write that is write that square root of x as x to the 1/2. I could bring that up out in front as x to the negative 1/2. So this and this are the same thing. And I do that because we like to have powers, because we have this new rule called the power rule. And remember what we started with. Sure enough, square root of x is x to the 1/2. You bring the 1/2 down, you drop that by 1, you get that. And so, okay. So we showed the power rule works with fractional powers. It works with negative powers. We did one with x cubed and x squared. It worked with those powers. Okay. And we got some practice at some different algebra things that we're going to need to do. Okay. The conjugate method, the bow tie or common denominator method, factor and cancel. Okay. I've got some sheets here. We got some things we'll practice out a little bit more as well. Okay. All right. Obviously, I had number 46 down here to do. Any others you want to do? Now, this would probably be a good time to show you this. Why don't you go ahead and get your calculators out? Our next quiz will probably have both parts, calculator, no calculator. But not to do this thing I'm going to show you right now. You're not going to use them for this on the quiz because this would be silly. That'd be kind of like teaching 4th graders. When do you learn division and multiplication? Fourth grade? 5th? 4th? 3rd? 3rd maybe? 3rd is multiplication division. Okay, whatever. So let's say you're just learning multiplication division and the teacher lets you use a calculator, right? Well, you're not going to use a calculator when you're learning multiplication division, but then you get into algebra, and then yeah, you can use a calculator because why would we want to spend a lot of time adding up 5-digit numbers? Well, now we're just learning some rules for doing derivatives. The calculator, and this is the CAS part of this calculator. So if you took one of the yellow, AP Stats calculators, they don't do this thing. But if you go onto your scratch pad here, and we go next to the 9 here, I call this the template button. It just got some different templates for various things. Have we been in this button before? I can't remember. I think I showed you absolute values in here. This vertical bar over here by the equal sign does not do absolute value. So I showed you the absolute value. There's square root in here. There's powers in here, but we've got these power keys, so we don't use them for that. But the one we want is this guy right here. Okay? Notice it's in that Leibniz notation that I showed you the other day. And then the one next to it is second derivative. Right? See that? So right here, hit that. Okay, and that puts that into your calculator screen. And that is the derivative. Okay, so now we would usually use x. Now, they're not always going to be with respect to x, but sometimes it might be with respect to t. So whatever your input variable is in that particular function is what goes there. And then in here, you put what you're trying to do the function of. So let's do like sine, for example. Let's put in sine x. Get in. Look at that. The magic derivative machine right here. Okay, so that's a wonderful thing. So we want to do, you want to check number 17, 3x squared plus 4, 3x squared plus 4, hit enter, 6x, right? So what you have here basically is an electronic solutions manual for your derivative, right? So when you're doing these derivative problems, practicing for our derivative test that'll be in chapter 3, you could use your calculator to check, but you're never going to get it. I mean, there's going to be problems. Anytime we're doing a calculator test and you need to do a derivative, you can use this to do it. Now, what I'm not going to do on a calculator test is give you a bunch of problems, say, hey, find the derivative, and then just let you use your calculator. That'd be silly. I don't care that you do that. But there's going to be problems later on where you got to do the derivative, set equal to 0, then do some other stuff and find local maxes and mins. Then if it's a complicated derivative, you can use a calculator to do it, so that's fine. But for the quiz next time, you're going to have some problems like this where you have to use your power rule to do some derivatives. That, of course, is going to be on the no calculator problem. But while we're doing our homework, you should do them without a calculator, and then use this if you're unsure. Use this to check it, okay? All right, anyway, any of those you would like to see or you weren't sure about. Now, obviously, you only could see the odd ones probably in the back. I know many of you took pictures of the solutions manual, so maybe you were able to see all of them. But does anybody have one of those that they just thought, you looked at the solution manual, you weren't sure why it got that or anything like that? Now, we'll do 46, but any others? 23, okay? So 23 says, and while you guys are at it, while I'm writing this down, why don't you take 23, some of you anyway, take 23 and do the derivative of it in your calculator now that you know how to do it. Let's just see what's up with that. But while I write this here, so f of x equals 4 square root of x cubed minus 5x to the negative 2/3, right? So this would be a problem that I could give you on the next quiz and tell you to just find an f prime formula. Now, I should have mentioned this yesterday. Now, I didn't look like anybody was doing this. I maybe did on a calculator. It says check the reasonableness by comparing graphs of f and f prime. So that's what we did yesterday. Remember when we found a couple of those, I drew a quick graph, and I looked at it and said, oh yeah, it makes sense, because when f prime is positive, the negative f is got. So that's always a good thing to do, to double check and practice your chart and all that kind of stuff. But when it says that on the homework, that's fine. Try it if you want on a couple, but I wouldn't worry about doing it on a whole bunch of those, okay? But I might ask you that on a quiz. That would be a good question for the calculator part of the quiz. Give you one like 23, have you do the derivative and say, sketch their two graphs and explain why it's reasonable that is the derivative. And then you kind of make some of those chart kind of comments, right? So you graph f prime on your calculator, sketch it, and then discuss it. So that would be a good question, right, to have you do. All right, so anyway, first thing I would notice on this one is we want to get that into a power. So I would change that to 4x to the what? That'd be 3 halves, because remember, this root is always the denominator, okay? So now when I do my derivative, I'm going to bring that down. Yes, you're going to have to do some fractions without a calculator. So 4 times 3 halves, let's remember what we do with fractions. We multiply straight across. Now you can reduce, right? But you can just multiply across. That's going to be 12 halves, which would be 6. X to the, you subtract 1, so 3 halves take away 2 halves, right? So that would be 1 half. And then we're going to bring that down. That's going to turn that to a positive. 5 times 2/3 is going to be 10/3. Usually we just write that as improper. That's probably a better way to do that. I don't want decimals rounded. You would definitely have to go 3 decimal places if you did that, but I think that's a bad habit to get into. Let's write it that way. And then that would be x to the, and that'd be negative 2/3, take away 1. So take away 3/3, so what's that? Negative 5/3. So we do need to get kind of good with working with those fractions, adding and subtracting, right, without a calculator. Okay, so we got to make sure we do that. Now, again, I always get people when they're trying to subtract or add fractions that they multiply the bottom something, or they do some weird things. So remember, when we multiply, we just multiply straight across and then reduce. I think that's the safest way to do it. It just depends how comfortable you feel doing that. Okay, so that'd be it. Now I'm curious, what do we get on the calculator with that one? Somebody want to read it to me? Who's got it?
6x squared divided by
6x squared.
6x squared divided by the square.
Oh, okay.
That's divided by the square of x to the 3rd plus 10 divided by 3x to the 5/3.
That's the answer, right? So here's the problem with using the calculator to check these. So you work it out, and then you go to your calculator and it says this. You got to understand that the calculator is going to simplify it in different ways under rules that it's programmed to do. Okay, so one way to do this would be to just look at this and double check and say, okay, I see my 6. This would be 3 halves, right? So 2, what do? You subtract the powers, right? So 2 take away 3 halves, well, that's 1/2. 2 take away 1.5, that's 1/2. Okay, that fit. Here's my 10/3, and then this is on the bottom. It would go to the top. It'd be negative. Okay, I got the same thing. Now, if you're not comfortable with that, here's another thing you can do. So everybody, if you've got that on your calculator right now, that answer that Harish just read to me, go up and grab that. Go up and grab that answer. Hit enter. So go up and so it's highlighted. Hit enter. Then put an equals. And now type in this answer right here. Now type in the one we just got. With me? So you let the calculator do it. Get its answer. Grab it. Hit enter so it's down there. Then put equals. Then type in your answer. And basically what you're asking the calculator right now, does this one that you got equal the one I got? And you should either get true or false. Now sometimes that is a little bit iffy because there's some domain issues sometimes or whatever. And so it's not a perfect scenario for checking, especially on some more complicated ones, but it's better than nothing. Are you getting true?
I didn't get it. It didn't say true.
That just gives you the same.
Okay.
If you scroll up.
All right. Well, shoot. Every time we change this operating system, so you don't get anything. It just. All right. Well, let me see. Okay, let's try this. Okay, so let's grab that. Oops. Okay, I'm going to try this. Let's try doing this. Let's do a solve. I'm going to grab that. Let's do it that way. Let's do a solve. So I'm going to do a solve and then grab that. Grab that. So I'm going to solve, and I'm going to grab what we just typed in with the one thing equal the other thing. And then I'm going to go comma x. And if the two sides are the same, okay, they're not so true. So that's like doing solve 2x equals 2x. Well, that's always true. Okay, so the solution is all numbers, right? It's always true. So do it that way. So do a solve, grab this one, equal to this one, comma x, and if they're the same, you should get true. Now again, sometimes they're not because of how it's written with domain issues or something with an x in the bottom. The calculator might not quite give us what we'd expect. So again, not a perfect scenario, but it should work. But that time it said true. So that means, okay, so then you're like, okay, that is the right answer. Because I don't care. I don't want you rearranging this. When we do our derivative rule on our next quiz, and I say do the derivative, you just leave it like that. Now, do I want you to simplify it? Yes. I don't, like right here, we got 12 over 2. I don't want you to put 12 over 2. You need to put 6. Okay? So you need to reduce those things and do that kind of stuff. But we're not going to rearrange and put it back into radical form or anything like that. We'll just leave it the same. Okay? All right, let's talk about 46. So 46 was f of x was equal to square root of x minus 3 all over x. So what do I got to do? Ideas. Bring that x up as x to the negative 1. Cannot do my power rule right now. Okay, again, like I was saying yesterday, you can't just take this power rule, like make this x to the 1/2, sure, that'd be fine. But you can't just start everywhere you see an x with a power, start doing the derivative to it. That doesn't work. Okay, remember we showed yesterday, if you have this function times this function, you can't just do this one's derivative and this one's derivative. The same thing's true when you're dividing. You can't just take that top derivative, do the bottom derivative, and then be done. It doesn't work. Okay, a real simple example would be this. X cubed over x cubed. Well, what's x cubed? That's a bad example. Let's do x to the 8th over x to the 3rd. Now, what's x to the 8th over x to the 3rd? That's x to the 5th. Well, what's the derivative of x to the 5th? 5x to the 4th. We know that should be our answer, right? But if I do this and do 8x to the 7th over 3x squared, that gives me 8/3 x to the 5th. Well, that is not the right answer. So you cannot just do the derivative up here and the derivative down here. It doesn't work. Okay, it doesn't work. So it's the same thing with times that we talked about yesterday. You can't do it with multiply or divide. So what we need to do is we need to, now here's what almost everybody always thinks of when we do this problem every year. When we bring this up as x to the -1. So let me do it that way. Let me do it Harish's way, and let me show you a better way. And not really. This way is just fine. But there's going to come a time later with some stuff we do where there's another way that's just a little easier. So, or makes a little more sense, I think. So we bring that up as x to the -1, then we distribute. So what do you do with the powers? You add them, right? So this would be x to the -1/2 minus 3x to the -1, like that, right? So you bring that up and do that. Now that's still f. Now I should have been labeling this all the time. You got to be really careful here with our work. Okay, so that's f. So all I've done is rewrite f. Now I'm going to do f prime. Okay, so I bring down the -1/2. That'd be x to the -1/2 minus 1 would be -3/2. And then bring down that -1 and turn to a positive 3x to the, and then just stop right there. Just leave it just like that. Just leave it just like that. Okay, now, let me show you in blue how I would suggest we probably do it from here on out. Okay, first of all, we rewrite this as x to the 1/2. Another thing you can do with fractions, keep in mind, if I have 3/7 plus 2/7, right? We all know that's 5/7, right? We can put that together. We can put that together as 3 plus 2 over 7. Everybody agree with that? Well, we can do that in reverse also. Whenever we have a single denominator, now you can't do it the other way. If you have 7/3 plus 7/2, right? That's not the same as 7 over 3 plus 2, right? We can't do it the other way, but when we have a single denominator with some terms up on top, we can go this way and we can, what I call, split it apart. We can split apart the fraction, but we can't ever split a denominator. So you can't go from here to here. That doesn't work, right? That doesn't work. You can't split apart a denominator, okay? But if you have a single denominator with terms on top, you can split apart the fraction with that single denominator. And I think that for a lot of things we do this year, that's going to be a good thing to do. So I can take x to the 1/2. Matter of fact, most of the time you'll do this in your head. So we can go x to the 1/2 over x minus 3 over x. We just split it like that. Okay? Well, now here we subtract those powers. So 1/2 take away 1, that's x to the -1/2. And then 3 over x, we're going to write that way because we want to do a power rule, so we want to write it like that. So I think the way I'm going to suggest doing it from here on out, you got a single denominator, we're just going to split it. Just going to split it. Okay? Subtract the powers, and then you're down to here, and then you go. So it's not really any faster, it's about the same, but it just seems to be a little easier to work with when we get into some problems later. Okay? So take a fraction like that, split it apart, and then go on your way. All right, let's talk about, so we'll get a little more practice on some of those things. Anything else? Any others? I'm sorry, I didn't really give you another chance to ask on another one. 45. 45 you would FOIL out first. So on 45, you would want to FOIL that, get 3x squared, what is it, plus 2x minus 8. So that's f. So f prime would be 6x plus 2,
Let's just see.
and then just 0, right? So FOIL it first. So the lesson on both of those two problems, on 45 and 46, is before we can do the power rule, there's oftentimes we have to do some simplifying of our function to get it into a form that fits the rule, okay? So we want to get it into where we have some individual terms that we can do the derivative of each individual term, okay? So, and then the same thing is true on, I didn't assign 47, I don't think, right? But look at 47, we would just split that up, right? We would just split that up, put each of those terms on top of x to the 1/2. Or on 48, we'd square the top, square the bottom. That's one of the rules with squaring a fraction. You can square the top, square the bottom. Then we would probably FOIL out the top. The bottom would have an x squared, and then we would split it apart, right? So we would do all this algebra to it to get it into a look where we could do our power, okay? So that's something we would sometimes have to do before we can do the derivative. We would need to do that, some simplifying, okay? All right. You know, with that -8 there, I'm just kind of curious. What if I had another function that was 3x squared plus 2x plus 10? What would the derivative of that be?
Same thing.
What if I had 3x squared plus 2x minus 1? What if I had 3x squared plus 2x? Those would all have the same f prime. How many f's could I write that have that same f prime? Infinite. What is different in all 4 of those f's? What's the only difference? Think of the graph. Wouldn't those just be vertical shifts of one another? Hold on a minute. In chapter 1, when we were graphing f primes, we started with a single f prime, like 6x plus 2. And we said we're going to draw the f graph. How many f graphs went with that at one f prime? Remember, we didn't know where to start? We said if we know the f prime, we know the slopes, but we don't know where to start. So we pick a point, then we would do it. And we said there's an infinite number. They're all vertical shifts of one another. Oh, well, there we go. That just shows it right there. That just shows it right there. This f prime goes with all of these f graphs because that plus c, that number at the end, some constant, is just, you know, the vertical shift. And when we do the derivative of it, that constant goes away. Okay, now this kind of ties in with something we did before. All right, get your notes out. Let's talk about this idea of a limit. So what we're going to do is do a little bit of a side trip here for a day or two. Section 2.3 is a little bit of a side trip into the idea of a limit. So we're going to kind of get our head away from derivative here for a little bit. Okay, because what we're saying is the only way we can do the derivative is which is the slope at one point. The only way we can do the slope at one point is use this idea of a limit. First time you've probably heard of it. And so the idea of a limit is, and now you can go back to that question you asked the other day, is can you ever really get an answer? And of course, hopefully I convince you that yes, you do. The answer you get is it's really what the function, what the outputs are getting close to as x approaches some input, okay? And that is what we call our L. So, I mean, yes, theoretically, you can say you never really get there. But what we're going to say by our definition, this isn't really a formal definition, this is just the language, but we're going to say the limit is, or the answer is to a limit problem, this number that we're getting closer and closer to. That's what we mean by the limit. It's the limit. So you could argue, you could say you never really get there, okay? But that is our answer to a limit problem. That's our limit. That's what we're getting close to. That's what we're approaching, okay? So we read this limit of f of x as x approaches a equals some number f. So if a limit problem has a limit, it's a number answer. Now we do have some limits that do not exist, that they don't approach anything, okay? And we will say that. There are some limits that do not exist, okay? And you're going to see here, I've got a couple little videos that I kind of like that show this. All right. So another way of saying this, when we do a limit problem, is when we're doing limit problem, we're asking this question: what are the outputs getting close to as the inputs are getting close to some number a? So right now we've been doing h approaches 0, so our input has been h, right, for the definition of the derivative. So what are the outputs? And the outputs in our problem have been slope, right? So what are these slopes? So we got 2 points, and we're doing the slope, and we get closer, and we do the slope, and we get closer, do the slope, get closer, do the slope. Because our formula we've been using is a slope formula. So our outputs have been slopes. And as h gets closer and closer to 0, our slopes are getting closer and closer to whatever the slope would be at that one point, right? But this is a special use of the limit. The limit can be used for any function and for any inputs, getting close to any value, right? So we're going to take a little side trip. We're going to forget about derivatives here a little bit and that limit, and we're just going to talk about limit problems in general. So as we move forward today with our homework, with these videos we see, you can just kind of forget the idea of slope, forget the idea of derivative, right? That's not what we're doing. We're just going to investigate this thing called limits, and then try to understand it a little better. Okay, that's what we're doing. All right, so here is an example problem. All right, what is the limit of x squared plus 1 as x approaches 2? So I went ahead and graphed it because it's always nice to think graphically. I think limit problems are easiest to do if you have graphs. So when you get a limit problem with a graph, I think those are the easiest ones to do. The ones we'll have the harder time with are the ones where we have equations, right? Because just visually it's easy to see. All right, so here's x squared plus 1. Parabola shifted up 1. As x approaches 2, now another thing you're going to hear me say here when we talk about limits is we're going to be talking about as x approaches 2 from both sides. Okay, because we're going to talk about limits from the left as x approaches 2 from the left and as x approaches 2 from the right, because sometimes they're different. So when we say x approaches 2, we're just assuming we mean from both sides. So as x approaches 2, what are the outputs approaching? What value are the outputs approaching? 5. Don't overthink it, right? 5. So as you get an x really close to 2, you're getting an output really close to 5. You get an output on this side of 2 really close to 2, you're getting an output really close to 5. As x is approaching 2, that function is approaching 5. Now, could we just plug in a 2 here and get a 5? That's easy. It seems like a big lot of nothing for something just so easy, and that's true. On some problems, this is a pretty uninteresting limit problem because all you have to do is plug in a 2 and get a 5 and you get the answer. Okay, so that's called direct substitution. So the first thing you always want to try in a limit problem is direct substitution. Now, what happened to our problems when we tried to put a 0 in for h? We got 0 divided by 0, right? Most of the time in most limit problems that are interesting at all, when you try to do direct substitution, you get 0 divided by 0 or something weird happens. Okay, and then we have to investigate further. Okay, so that's what we'll spend most of our time doing. But this would be the easiest of easy limit problems. We would just do that. Okay? All right, so what about this one? So don't look at the graph just yet. Just look at the limit problem. So what's the limit of this? We actually did this one the other day. We did tie this one into derivative, actually, but just forget that for right now. What if I just ask you this problem? What are these outputs approaching as the x is approaching 3? Why you say direct substitution? Let's try it. You plug in a 3, what do you get? 0 divided by 0. Okay, but then if you graph this, something brand new emerges. If you graph this, it turns out to be that line with a hole in it. Yes, it is. That is a graph. There are graphs that just have that are a basic graph everywhere except one place has a hole in it. And that's what this is. At 3, there's a hole. It's undefined. Well, it's pretty easy to see. Remember when we said x plus, we said we would factor this? Remember that? And then you would do this, right? Well, what happens when you cancel that out? What are you left with? X plus 3 which is what that line is. So that's why this graph, see in algebra class, if I gave, forget limit, in algebra class if I gave you this and said simplify, what would you do? You'd do this right here. And then you'd say this is equal to this, but are they really equal? They're equal everywhere but when x is 3. This one, when x is 3, is undefined. This one, when x is 3, you get 6. So they're equal everywhere but when x is 3. So that's why the graph of this looks like the graph of this, except when x is 3. There's a hole because it's undefined. But back to our question now with limit. What are the y values getting close to as the x values get close to 3? They are getting close to 6. But do they ever get to 6? No, there's a hole, but we don't care. We don't care that they never get there. Well, the question is what are they getting close to? They're getting closer and closer and closer to 6. So that is our answer. That is the limit. The limit is 6. The limit is not what they get to. The limit is what they're getting closer and closer to getting to. Does that make sense? I mean, it's back to your question. Do you get an answer? Yes. Even though there's a hole there, yes, we get an answer because the y values are getting closer and closer to 6. So we say that is the limit. So the limit is 6. So the limit does exist here. We can do, so why are we practicing this algebra? Because we can do a little algebra. We can get here. Now we can do direct substitution. 3 plus 3 is 6. All right. Just so you can hear it from somebody else, I've got these little videos that I think are kind of fun, and they do a pretty good job.
You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height.
Now we gotta hear the whole thing.
You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot, so we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height.
Okay, so I like that idea. What does it intend to get to? That graph there, clearly at 3, the graph was intending to get to 6. Okay? It just didn't because there was a hole there. But that's where it was going.
Let's start by looking at a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I am getting very close to the x value of 2, my function is getting very close to the height of 4. There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take for example this function, g of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, negative 2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of negative 2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to negative 2. This begs the question, when exactly does the limit exist? We examine that in the next module.
Okay, so that's kind of what we were just talking about. Okay, so
You may have
we were just saying that you got a hole, graph's trying to get there, the limit exists. So what's it look like when a limit doesn't exist?
Now you have some idea of what a limit is, and we need to talk about when does a limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x. As long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists. Now it's time to get down to the brass tacks and look at this
So think about
mathematically.
piecewise functions.
Take a look at the graph of this function f of x. Visually you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However,
Even though
if you
there's a hole
travel
there,
towards
I
4
don't care.
from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right the right-hand limit of f of x, as x approaches 4 from the right. And we denote this with a little plus sign
there
in our
means
limit
from the
symbol.
right.
Our height that we arrive at from the left is called the left-hand limit of f of x, as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal.
Okay, so something you might jot down in your notes. For our purposes, the left and the right-hand limit will always exist. The left and right-hand limits will always exist. Now, that gets a little bit fuzzier when we get into chapter 4, because if you have an asymptote, like tangent, let's say, the car on the left might go to infinity, and the car on the right might go to negative infinity. They don't meet, but we would say the left-hand limit is negative infinity, the right-hand limit is positive infinity. And technically that isn't a limit, because a limit's got to be a number, and infinity's not a number. Now, we're not going to deal with infinity right now. That's going to be in chapter 4, so we won't get into that. But right now, we would always want to write down either a number or infinity. So basically, right-hand limit and left-hand limit will always have something. have some answer, but the limit itself only exists if the left and right are the same. In other words, if the cars meet. So the left-hand car is going to go somewhere, the right-hand car is going to go somewhere. The question is, do they meet? Okay? And then if they do, then the limit exists. So for the limit to exist at 4, the left and the right, and that's why I was drawing those arrows, as x approaches 4 or whatever, from both sides, the y values have to come together, and then that is your limit. If they don't come together, limit does not exist. Okay?
Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrived at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
So I like that thought, of the diner burning down. That's kind of like the hole in the graph. The cars still meet there, even though the diner's not there, the cars still meet. Okay? And then finally, finding limits, especially when you don't have a graph
whether
to
or
look
not
at.
a limit exists. The next logical step is to try to figure out what the heck that limit is. So that's what we'll be focusing on in this section. How do you find a limit? The fancy word for finding the value of a limit is evaluate. So when you see the directions evaluate, basically you should be expecting to get a numerical answer. There are 3 major ways to evaluate a limit. They are substitution,
We have
factoring,
4. The bow
and the conjugate
tie.
method.
He doesn't have the bow tie.
We're going to go
That
ahead
would be
and
our
start with the easiest one, which is direct substitution. It is just as easy as it sounds. We'll take an example. Here's one. The limit as x approaches 0 of the fraction x squared minus 1 divided by the quantity 2x plus 3. In order to evaluate this limit, all you've got to do is plug in 0 everywhere you see an x. So we'll put in 0 in the numerator and in the denominator, and we end up getting negative 1 divided by 3. So our limit is negative
If you
1
can do
third.
direct substitution, get an answer right away, that just means it's a basic graph, no hole, nothing weird going on, and then that's your limit. Doesn't happen very often. Now, one thing you want to be careful of is when you get into all the factoring, because most of the problems we do are going to involve some sort of factoring or something like this. So you're going to get a problem like this, and right away you're going to think about factoring, right? The problem is, the only time you need to factor is if this one is the limit as x approaches what? 2. Because then you would get 0 divided by 0. But I might just throw a curveball at you and just give you this problem and say, what is it when x approaches 3? Right? Now, it turns out you'll still get the same answer. You'll just do some extra work you didn't need to do. Right? But here you can just put in a 3 and you get 5 over 1, which is 5, and that's the answer. Now, if you factor and cancel, the x minus 2's cancel, you'll get x plus 2, and then 3 plus 2 is 5. So you still get the right answer. But the point is, you should always try direct substitution first. Okay?
Fortunately, not all limits are this easy. And you've already seen one for which that's the case. Remember that function that we were dealing with in the first section of this chapter? In case you don't, here it is again. The limit as x approaches 2 of the fraction x squared minus 6x plus 8, all divided by the quantity x minus 2. We looked at this before. it had a hole in it at the coordinate 2, negative 2. And we concluded from that the intended height was negative 2, making it the limit. However, it would be nice to be able to figure out why this is true mathematically. And to do that, we'll have to use the factoring method. As you can see, and as we saw before, direct substitution results in 0 divided by 0, which is not allowed. So we'll have to resort to this new method. We'll use the factoring method because the numerator of this fraction is factorable.
Anytime you do direct
If we
substitution,
factor
get
it,
0
we'll
divided
get
by 0,
x
that's
minus
basically a
4
sign to
times
keep going.
x minus 2.
There's
Can
probably
you
a
see why that's a good
limit.
idea?
Keep
Well, the reason
going,
is
fine.
because now the numerator and the denominator both contain the term x minus 2, which I'm going to cancel out. This leaves the limit as x approaches 2 of x minus 4. This is much simpler to solve because now you can use substitution. And when I do, I get 2 minus 4, which is equal to negative 2. Remember, we knew the limit was going to be negative 2, and we're right. It feels good to be right.
Alright, almost there.
If the substitution method fails and the factoring method fails, you're not without hope. You can still try the conjugate method. Before we talk about the conjugate method, though, we might as well figure out what a conjugate is first. Take a look at this expression, the square root of x minus 4. Now, this is a plain old two-term expression. However, it is easy to make a conjugate. All you do is change the negative sign in the middle to a positive sign. The conjugate of the square root of x minus 4 is the square root of x plus 4. That's all there is to it. Now, what if you see an expression like this in a limit problem? For example, this limit problem. The limit as x approaches 16 of the fraction, the square root of x minus 4 divided by the quantity x minus 16. Well, what we'll do is multiply the top and the bottom of the fraction by the conjugate of the radical expression, which, as we said, was the square root of x plus 4. Now, the magic of this is that as you multiply out, the numerator will actually become x minus 16. You don't want to multiply the denominator out. Leave them as separate factors. Since I have x minus 16 in both the numerator and denominator, I can cancel them, just like I canceled like terms in the factoring method, and I'm left with the limit as x approaches 16 of 1 divided by the square root of x plus 4. Do you see why we didn't want to multiply out the bottom? It makes simplification much easier. Now I'm able to plug in 16. Substitution works. When I do so, I get 1 divided by 8. So the limit as x approaches 16 of my original function is 1/8. And that's the conjugate method.
Alright, sum up.
There you have it. There are 3 major methods for evaluating a limit. Substitution, which is the easiest. Factoring, which is useful when either the top or the bottom of the fraction is factorable. And the conjugate method, which is useful for radical fractions.
Alright, so, for our homework, we'll look at what does that mean for us now going forward? What kind of problems are we looking at? Well, we're going to have some where you're going to have some in the book where you have some graphs. Now, for us, when is the limit not going to exist? Well, when the cars don't meet. So if I give you a graph that goes like this, and then goes like this, and then goes like this, and then does that, and then goes here like that, right? There's a couple of places the cars don't meet, right? The limit's not going to exist right here, and the limit's not going to exist right here. But right here, the limit will exist, whatever that y value is. Now, sometimes we get a graph like this, okay? Now, that would be the equivalent of the diner has burned down and has moved to a new spot. Well, where do the cars meet? At the old spot, at the old diner. So let's say this was a y value of 2, and this was a y value of 3. What would be the limit there? 2. They meet at 2. That function intends to reach this y value here. It actually reaches this y value. There'd be a case where the function's output is actually not the limit. Again, we don't always care what the exact y value is at that point. What we care about is where do the cars meet? Where is the function trying to get to? What is it getting closer and closer to? The y value that this function is getting closer and closer to is this y value. The actual y value of the function is that, but not the limit. The limit is is right down here. Okay, understand that difference. Now, many times, if there is a y value and that in a normal function, you know, the y value and the limit are the same. Okay, but that would be a case where it wouldn't be. Okay, of course, you're not going to do direct substitution in one like that because it's going to, if a graph looks like this, it's going to be a piecewise. It's going to be really easy to know what that function is because it's going to be a piecewise kind of thing. So it's going to give you some some things like that. Then we're also going to have some equations. And I got a worksheet here with some equations where you're going to have to bow tie or conjugate or factor. Now, the only time you should ever get does not exist, when you get 0 over 0, you're probably going to do your algebra, whatever algebra you need to do, and then you'll eventually get an answer. Just like there, he had 0 over 0, then he did his algebra, ended up getting 1/8. Okay? If you ever get 6 over 0, or 2 over 0, or -2 over 0, or something like that, for now, then you can put does not exist. Because there's nothing more you can do at that point. Now that's when we get into infinity and we get to chapter 4, we'll talk more about the infinity situations, okay? But for right now, that when is a limit not going to exist? Well, on a graph, it's going to be when the cars don't meet. So the limit doesn't exist here, the limit doesn't exist here, the cars don't meet. If you're working out a problem with algebra and you factor some things, and then you go to plug in with direct substitution and you get this, 6 over 0 or some number over 0, then you can say does not exist. But if you're getting 0 over 0, that means keep going. That means there's some algebra that can be done to get to an answer. Now sometimes you plug in, you get 0 over 0, you do some algebra, and then you plug in and then you get 6 over 0. Then you would say does not exist. Make sense? Okay, so the next line in the on the assignment page there says 2.3. Now, the 1 through 3 and then number 7 in class, that's part of your assignment, okay, with the question mark. So do 1 through 3, number 7, 13 through 26, 39 through 42. And then this worksheet here, which is just some algebra limits. So the idea is you wouldn't use your calculator on this. Under that template button, by the way, if you want to do some checking of this, that template button where we did the derivative, there is a limit template that you can do, these limits there too. So as a check, if you want to see how you're doing, you could type them in to check. But the idea is on our next quiz, you will have problems like this on the no calculator part. So if you want to kind of stick with what you just saw in the video, you might want to do the worksheet first. I don't know, it's up to you. Or you can do the book problems first as well. I will say on 1 through 3 and 7, those do relate a little bit to the derivative, okay? Remember I said we're taking a side trip and not really doing the derivative? Those relate to this thing we did the other day, this alternate version of the slope, because they kind of look like this. So it kind of refers to that alternate version of the derivative that we had. Okay, because that's really just slope between 2 points. One of them is A, one of them is X. And the 2 points are getting close because X is approaching A. Okay, so there is a little bit of a connection back to derivatives there. But otherwise, the rest of them are just kind of limit problems. The worksheet will be graded just like homework is, kind of completion. I'll look at it on Monday if you've got some questions. But again, if you're really struggling on some of those things, I'll be here early Monday morning.
Round up the answers. But spaces. Hey, yeah, somewhere. Shut up. Oh, hey, James, that was really funny.
No, it's James.
James. Oh, okay. Jace. Yeah. Did you get what's that?
Yeah, so I got.
Yeah.
I like the answers. Do we just say great limit of whatever equals something, like for notation wise? Or how would you write it out? Like,
Say that again now.
for like notation, would you just like write limit of x approaches something equals a value? Is that like how you're supposed to?
Well, you mean if they ask?
Well, just
I'm
like,
not following.
okay. So would that be the correct limit?
Well, it should be limit. I mean, to be honest, you could just put equals, you know. In other words, there should be something there. She should always put function there. So it's really the limit of some thing, right? So really the generic, what I wrote down earlier is, you know, right? There's something in here. So this would be our function we're doing the limit of, right?
Oh, you put the original function in there.
Well, if you wanted to really write out a proper final answer, it would be all of this equals 5. Or just work this out and then just put your 5 right there.
Oh, that's true.
Just circle, you know. That's kind of why I wrote
But
it.
she told
So,
me you
yeah.
can't do that. They had did that. But you should do it on by the right. I got this wrong.
Yeah.
Do you know how many of the answers are